Okay, so the other part of Unit 3 was circular motion, because that's also motion in 2 dimensions. This PowerPoint actually combines circular motion and gravity, but I'm just going to do the circular motion part. So we'll cover kinematics of uniform circular motion. I'm also going to touch upon some dynamics of uniform circular motion, even though dynamics really comes in Unit 4 because you've already learned them, so we can do that. And that includes highway curves, banked and unbanked, the forces that exist on those. So in uniform circular motion, you've got motion in a circle, constant radius, constant speed. Your instantaneous velocity is always tangent to the circle, so a lot of times it'll say like v tan or something like that. This is also comes in dynamics. If you're spinning this around and you've got the ball right at the top, if you were to cut that string, the ball would follow that tangential velocity path and then become a projectile. So we've got mass moving in a circle at constant speed. We know that acceleration is the rate of change of velocity with time. Now, if we're moving at a constant speed, the magnitude of the velocity is remaining the same. The problem that we have, though, is that the direction is constantly changing. So we know there has to be acceleration. However, the magnitude of the acceleration is not going to be a tangential acceleration in that the velocity is changing. It's a little bit different. So things that we have happening is you find that in order to keep changing that velocity in that circular direction, so it's here, then it's here, then it's here, then it's here, then it's here, there's this constant acceleration that's happening, and it's always towards the center of the circle, right? Center seeking, centripetal. Okay? And that centripetal acceleration, it's always happening right along the direction of the radius, right? It's always happening right there. Okay? So we can see that it's radial acceleration, centripetal acceleration. They're often used interchangeably. Okay? And so when we break it all down, we know from our studies before that centripetal acceleration is v squared over r. And if you're moving in a constant radius with a constant speed, you're going to have a constant centripetal acceleration, v squared over r. That v being the tangential velocity. Okay? Now, what about period and frequency? Well, period is going to be how long it takes to make one revolution. So one time around. Okay? How long? The time period. Students don't struggle with this so much anymore, but it used to be something that people would mix up a lot. So I always say, think time period. That's why we get the capital T. It's time. It's going to be measured in seconds. Okay? Frequency is how many times we go around per second, right? Frequency. So it's the inverse of the period. Okay? And we can actually use all of this to our advantage because, see, we remember that from Unit 1 or Unit 2, our one-dimensional kinematics, that if we have a constant speed, that constant speed is equal to distance divided by time. Well, if you're moving around in a circle, the distance is the circumference, which we know circumference is 2 pi r. So if we do 2 pi r divided by time, the period, we have our velocity. Well, the inverse of period is frequency, so we can also say it's 2 pi r times the frequency. And if we take our v value and plug it into our centripetal acceleration, v squared over r, we can then say that centripetal acceleration is 4 pi squared times r divided by the period squared. Okay? So if we're going to keep something moving in a constant circle, and we just said that means there has to be a constant acceleration. Accelerations happen when there's forces. So that means now we have to have a net force. So I'm pushing into Unit 4 a little bit here, but that's okay because that means then I don't have to go back and cover this later. So that force, it's a centripetal force that causes the centripetal acceleration. In the picture here, you have the force acting on the ball by the string. And that centripetal force is the tension force. Everybody loves to hear about tension. Okay? And we still follow Newton's second law that the net force is equal to m times a. A in this case being your radial or centripetal acceleration. So we can plug in that formula and say it's mv squared over r. Okay? So remember, it's that constant pull, 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 pull on the ball that keeps the ball moving in the circle. If it's a planet moving around the sun, it's the gravitational attraction between the planet and the sun pulling the planet back into that, well, not quite circular path, as we know from Kepler's first law of planetary motion, but pulling it into that curved path. Okay? And something to think about. Oftentimes, before you take physics, you hear about the centrifugal force, and everybody thinks, oh, it throws me to the outside and everything like that. Centrifugal force is what we call a fictitious force. It can only be observed in one frame of reference, and that's in the reference of the person actually going around the curve or the object going around the curve. But there's no action-reaction force, and it can't be observed outside of that frame of reference. Therefore, it's not a true force that follows all of Newton's laws of motion. And so really what it is, if you get outside of the frame of reference of that moving frame of reference, you see that it's really the centripetal force that's happening and the object wanting to fly along the tangent path. Okay? So here we have a ball moving around in a close to horizontal circle. It's actually, if you were to try to do the calculations, you cannot ever have an object move perfectly horizontally in the air because the tension force, there has to be some y component of the tension force to keep the ball from falling. So if you went perfectly horizontally, there'd be no force in the y direction to balance out this gravity force of the object. Okay, so if we look here and we have a mass of 0.15 kilograms moving around a circle with a radius of 0.6 meters, it has a period of 0.5 seconds, and let's for the moment just assume it's in a horizontal plane, just to make the math easy. We could find the force of the tension, right, by using Newton's second law, F equals ma. Okay, and in this case, it's the tension force, and A is centripetal acceleration. So m times v squared over r. Plug in our v, plug in our t, or we plug in our r and our t values to find v, and then we can find that we have a tension of 14 newtons. Okay. So now let's say we're moving in a vertical circle, right? Okay. Here's the thing. When we get to the top of the path, and everybody's always like, oh my gosh, this is why you kind of feel a little weightless if you go upside down in a roller coaster. It's because your normal force isn't like pushing you into the seat, right? Gravity is pointing down, and you've got something pulling you towards the center of the circle, the tension force. And so at the top of the path, the tension force is actually much less because it doesn't have to overcome the weight of the object. Whereas at the bottom of the path, you've got the weight down plus the centripetal acceleration. That tension has to provide both, okay? It's got to counteract the weight and provide the centripetal acceleration. So you've got a bigger tension down at the bottom of the circle than you do at the top. Okay? So here we have a radius of 0.72 meters, a velocity of 4 meters per second, and a mass of 0.3 kilograms. And so you can see how we can find the tension force both at the top and the bottom, okay? Where your sum of the forces is equal to mass times the centripetal acceleration. And so on the top, it's the tension force plus the weight that is providing the centripetal force. So the tension's much less. Whereas on the bottom, the tension minus the weight is going to be the centripetal force. Okay? And so this happens on a Ferris wheel, okay? For a tethered ball, okay, we can look at just the circular part, right? And we can break things up into our different components. Okay, on a curve, if you've got a flat curve, okay, a curve that you're going around and it's completely flat, the only thing that's keeping you in that curve is friction. Friction is what is providing the centripetal force. So that's why you have to slow down on a curve, because you've got to rely fully on friction to stay in that curve. And so if you take a curve too sharp, there's not enough friction, or too fast, there's not enough frictional force to keep you in that path, and off you go. Same thing. That's why on-ramps and exit ramps are so bad in the winter when you've got ice. Your friction's so low. And so you see people whoop, slide right off. Okay? Now, a way we can help with that, and this is what you often see on those exit and entrance ramps, is banking the curve. Because when you bank the curve, not only do you have friction, but now part of the normal force, right, 90 degrees, part of the normal force from the road is pointing into the center of the curve, and therefore it's helping keep your car on the road. Okay, so as long as tires do not slip, then it's static friction. If they slip, you get kinetic friction. So two ways that's bad. Kinetic frictional force is less than static friction, we know. And the static frictional force can point towards the center of the circle, but kinetic frictional force opposes the direction of motion. So that means which way your car is going, that's the way the frictional force is. So if your car starts going, you know, kind of sideways, friction is going in not good, right? Okay, so here's that diagram I was talking about, how part of the normal force is pointing into the center of the curve to help with when you've got a banked curve. So if we have a banked curve, no friction, this would be our free body diagram. Okay? All right, I'm not going to get into universal gravitation until later, so hopefully that helps you a little bit with circular motion.